One of the most common devices that we use to test the output of an engine is what we call a dynamometer. We're actually going to get a chance to use dynamometers in laboratory in this class, and so I wanted to take some time to explain a little bit how they work and give you an idea of what kind of data we're going to get out of them and how to analyze that. So that's what we're going to do in this video. So this is one of the dynamometers that we have in our lab. We have two of them that are very similar. These are what we call power takeoff dynamometers. So they will connect to the power takeoff shaft on any tractor. So we can connect them to any of our tractors down there, and they measure the power output from the tractor. And this is actually one of a test chassis that we have in the lab, and some of you may be using that, and we'll use some other tractors as we go through this exercise. But the dynamometer in principle is pretty simple. So think about what we need to get power. If you remember, power was equal to torque times speed. We got to keep that in the back of our mind. So we need two things to be able to get power. We need to be able to measure the torque, and we need to be able to measure speed. So we need to know how much torque is on that shaft and how fast that shaft is rotating. And so the dynamometer is going to allow us to do that. And actually the dynamometer is what's going to measure the torque. The dynamometer in principle, again, like I mentioned, is very simple. And this is a picture of a simplified dynamometer. It's called a Prony Break. And that's not a misspelling. That is correct. It is a Prony Break. But it's simply a braking device. So what I need to do is I've got a rotating shaft. What I need to do is put some kind of a load on that shaft and try to stop it. So I'm just going to grab a hold of it. So, you know, we would obviously never do this, but you could just grab a hold of a shaft that is rotating and squeeze on it real tight, and that's going to put some torque on it. That's going to make it work harder. So you're putting some resistance torque on it. Remember, that torque is that rotational force. So that's what we're doing. We're resisting it. So this is the Prony Break concept. So the green shaft over here is my rotating shaft. So it's spinning here. This would be the output shaft of the engine or the power takeoff on the back of the tractor or whatever. And I've got this clamping mechanism, and the clamping mechanism is just going to clamp down on that shaft, and it's just going to grab a hold of it and try to keep it from spinning. So now what happens when I grab a hold of something that's spinning? It's going to tend to want to spin me, right? So if I clamp down on that with this device, it's going to have a tendency to want to spin that device. So what we do is have a long arm out here and hang a weight on the end of this arm, and that weight is going to counteract that twisting force or that torque that's trying to spin this thing around. So if I get enough weight to balance this thing out, I'll know, oh, wait a minute, torque. Yeah, what was torque? How do we calculate torque? We calculated torque as a force times a distance. Well, here you go, and it's even right here. Torque is equal to this weight that we have out here times the distance from that weight, where that weight is hanging on the end of the arm, back to the center of rotation of the shaft. That is my torque. That's how I measure torque. Okay. Now, what we do in lab, the concept of that dynamometer is very simple of what we use in lab, except we're not hanging a weight out on the end to try to balance a thing. We actually put an electronic force transducer on the end of the arm, and we can actually measure the force then electronically, and makes it easy for us. So this is the back end of that dynamometer, and here it is. This bar across the black bar with the silver on it, is that Prony Break arm, if you will. Inside this red box there is just simply a big old brake drum, similar to the brakes that are on an automobile or something like that. And they just grab a hold of that shaft and try to keep it from rotating. When that happens, that's going to want to rotate this arm, and right here then we have a force transducer, so an electronic sensor that measures force, and we have a digital readout, so we'll be able to see what the force is on that. So if we know the force that's being applied on this arm, and if we know the moment arm, so the distance from that sensor back to the center of this rotating shaft, then we know the torque that's being applied. So that's the way the thing works. So it's a fairly simple type machine. The big box you see underneath here, the big tank, that's just filled with water. So think about this. If I've just got brakes and they're just holding onto that shaft for a long period of time, that's a lot of friction. That's a lot of heat. And so we need to be able to get rid of that heat somehow. And so that we will actually pass water through this. We'll connect this up to a hose and keep water passing through this all the time to keep it cool. Otherwise, it would melt itself down. Okay, so that's what's going on there. The speed we'll measure with a digital tachometer. So that's pretty easy to get it with another handheld device. We'll be able to see rotational speed. We'll be able to measure torque. This is what we're going to come up with then. So this is a typical graph, and this is the performance from one of our tractors that we have down the lab. Some of you may actually be testing this one, but this is what it looks like. So we've got a plot here. On the y-axis is the torque. So I've taken that force and the moment arm, already multiplied them together and given me torque. So I've plotted torque on the y-axis, and on the x-axis down here I've plotted the speed, the rotational speed of that shaft in RPMs. The vertical here in these units are foot-pounds. And this is what the curve looked like. So typically the way we test these vehicles is that we'll turn them on, we'll open the throttle wide open so that the engine is running as fast as possible, and we start with no load on it, so we should have a high speed up here and probably very little torque. So we'll start up here actually with the test, and then we start to load that down. We start to put the brakes on, we try to slow it down, and as we do that, that's going to put resistance to that rotation. You'll hear the engine start to work and groan, and you can tell that it's slowing down, making a little bit more noise, and so the torque will come up and our speed will go down. And the torque will, if I keep loading it, the torque will keep going up. At some point, the torque won't go up so much, but it'll just keep slowing down, and at some point, it's too much torque. I've slowed it down too much, and the engine will just stall. So at this point, it just shuts off and it stalls. And we can stall with our engines. We can stall them and see how far we can go with them, and it won't hurt anything. So we'll be able to see that. Now, there's something kind of unusual with the shape of this curve, and I want to talk about that because this is something critical for us to understand about engine operation. The interesting thing about internal combustion engines is that unless you have some way to control them, they will run away and blow themselves up. So there's nothing, if you look at inherently the fuel intake and all of the timing and all of the ignition and everything, it's all based on engine speed. So the faster the engine goes, that stuff all works faster. And so without something to control the engine, it'll just keep going faster and faster and faster and faster. And you can get on YouTube and Google runaway engines and stuff like that and find all kind of videos of engines that just keep going faster and faster, and they will literally destroy themselves. They'll go so fast that something will come apart. It'll go beyond what it was designed to handle, and parts will fly out of it. I mean, literally, you know, rapid random disassembly. So just come apart and destroy itself. So that can happen. So we have to control it somehow. And all of our engines will have some type of what we call a governor. And a governor is something that governs the speed, and it works a lot of different ways, and we'll look later on at governor mechanisms and how they work. And some of them are electronic, some of them are mechanical, and there's different ways we can do that. But there's something that says, okay, we're going to control the speed. So there's going to be a set speed. So, you know, this is the maximum speed up here for this one. So it's a little bit over 600. So it looks like about maybe 615 or something like that, 620 RPMs. That's the maximum speed that shaft can be rotating. And at that point, the governor is controlling the fuel input somehow to the engine. And again, different engines, it does it differently, but it'll control typically the fuel input. And so if it's running really fast and I'm not requiring a lot of work out of it, I don't need a lot of fuel. And so that governor is going to shut down the fuel supply so that the engine doesn't run away with itself. Okay, now, so it's sitting up here nice and happy. The governor is pretty much shut down. There's not much fuel going into it up at this high point up here. Well, then I put a little bit of torque on it, and what happens? That slows the engine down. That torque is going to want to slow the engine down a little bit. The governor sees that, again, sometimes electronically with sensors, sometimes mechanically with centrifugal flyweights, and we'll look at all that later. But it senses that, oh, the engine slowed down a little bit. I'm going to open up and let a little bit more fuel go through. And then we load it up a little bit more, and the governor says, oh, I'm going to open up a little bit more. It's slowing down. Oh, you need more, you need more. So the more torque I put on it, the more that governor opens up and lets more and more fuel go into that engine until I get to a point, and you can see a real inflection point in this curve. So this curve is really straight till it comes up to this corner right here. So I'm going to mark that corner because that's a critical point, somewhere on that shoulder, if you will, of that curve. And it's at this point that the governor has opened up, and it's to its maximum. So whatever it was controlling, if it was controlling fuel flow rate or whatever, it's opened up, and it's like, this is all I can give you. That's it. So I'm wide open, and you're on your own after that. So we actually call this point right here, we label that the governor's max. So governor max. That means the governor is wide open. That's all it can do, okay? Now, this region of the curve above that governor max is what we call a governor control. So the engine is operating out here in the governor control. That means the governor is controlling the engine speed. And you can see different types of governors. You know, this governor is actually pretty good. It works pretty well in this engine. So this curve is pretty vertical. Sometimes the governors will be a little bit sloppier, and the curve may be tilted back a little bit or something like that. Some of our electronic governors on modern engines are very good. So that governor, the speed doesn't change hardly at all until I get up to governor's max, that it can't do anything more, okay? So that's the governor control out there. Typically a fairly straight part of the curve is what happens. Then we get this inflection point right here. Now the governor's opened up. It's not doing any more. It's just letting in all it can let in. This is what it can do. Out here, this is called torque control. So the speed is controlled totally by the amount of torque that I put on it. So the torque going in and out, that's what controls it. The governor's giving it everything it can, and it's just basically the engine is lugging. So we'll often talk about this being the lugging area down here. So this is torque control, or the lugging, L-U-G, for a lug. You know, I'm going to lug that engine, or how well. We'll talk about how well an engine can be lugged. And so the shape of this curve, you know, some engines can lug better than others. They're better at pulling things up hills and everything else. So there's a lot of different performance shapes that we'll have for different types of engines, okay? So one other thing I'll mention here, and let me draw another curve, just say that maybe this is what another engine curve might have looked like. So it looked like this, fairly straight line, and then it hit that curve out there like that. So this would be, you know, maybe another engine that I tested, just making up some numbers. You see that it got very straight line, fairly straight line coming up here. We have this corner point there. That's the governor max for that one. So, and this is governor control down here. But notice I specifically drew this not nearly as steep as this one. So this curve was a very good governor, pretty good governor, so it's fairly steep. This one didn't. So the governor was controlling, but that speed really could vary way a lot. So it could be lugged way down and so forth. We actually call this speed down here, we have a term for this. So this speed we call the droop, or the governor droop. So the governor droop is how far that speed, or how much that speed changes from wide open, from no load, up into governor's max. So this one has a lot of droop. This one here doesn't have very much droop. So if I drew a vertical line down from that curve, I wouldn't see a whole lot of droop in there. So it's only maybe, you know, 10 or 15 RPM, something like that. So it's pretty tight. This one's almost 100 RPMs, maybe like 90 RPM. So it's a pretty long droop. So that's what we call governor droop. Okay, so a couple of different things again. Governor max, we need to understand. We need to understand this region. So this is torque control down here. This is governor control down here. And then the droop is how far that governor can droop down. So those are the things that we want to look at on these curves, and we're going to see that. So be aware of that as we go and collect this data and test it. Okay? Now, let's look at these. Let me clear that curve off a little bit and look at it. So there's a couple other things I want to talk about. So where's the maximum power on this curve? Where do I get the most power out of it? Well, you know, we often think that, oh man, when we're lugging that thing down and it's really groaning and working hard, we're getting lots of power. So that's probably up in here. That's where we're getting lots of power. Remember, what does it take to give me power? Power is equal to torque times speed. So I need torque and speed to give me power. So down here, I've got a lot of torque, right? How much speed do I have? Well, I've lost a lot of speed. So I have lots of torque, but not very much speed. So I go up here, what about this end? I've got speed like crazy, so I've got a lot of speed, but I don't have any torque. So where's my maximum power going to be? The maximum power is going to be probably somewhere around this shoulder up here, where I've got lots of torque, lots of speed, and I'm going to get my maximum power point in there. So my power is going to be 0 down in here. My power is going to be fairly low down in here, and it's probably going to look something like that. My power curve is going to jump up. And in fact, if I plot them together for this tractor, this is what this power curve would look like. So I've got torque and power plotted on the same axis here, this same blue torque curve, and you see my power, very low, 0 down here, very low over here because I don't have much speed, but where I got lots of torque and lots of speed, so my peak power is right here. So I could actually draw the line down and say, okay, this is the speed at which I get my peak power performance. That's how much torque I get out of it, how much speed. So that's how we do that. This is the curve that we want to come up with. So in the class, in our lab exercise, this is what you're going to do. You're going to collect this data. We're going to take it to a spreadsheet. We're going to plot this out and look at how that tractor is performing. And I'll show you, I'll make a quick video, and for some of you that are not real familiar with spreadsheets and how to use them, how we can put this together. It's fairly simple to do that in Excel, so I'll show you how to do that. So that's where we're going. That's the gist of this whole lab, and it should be pretty interesting. It's usually a lot of fun to load these engines down and listen to them groan. We usually have a good time with that.